Welcome to This Explainer. Today, we're uncovering a pretty wild truth about the very ground beneath our feet. We tend to think of the Earth as a permanent, unchanging fixture, right? But the reality is completely different. It's actually a continuously evolving canvas, shaped and sculpted over millions of years by unimaginably powerful forces.
You know, we look at the majestic mountains, the deep valleys, and the vast plains around us, and they feel timeless. But if our planet's surface is constantly in motion, continuously breaking down and building back up, can any single landform truly be considered permanent? It's a massive question, and answering it entirely changes how we see the world.
To figure that out, we're going to look at our constantly changing planet, head inside Earth's engine room, check out the internal builders like plate tectonics, the external sculptors like weathering and erosion, look at how landforms evolve, and finally, talk about sudden shifts like natural disasters.
All right, part one, a constantly changing planet and the illusion of permanence.
Moving into part two, inside Earth's engine room, heat and pressure.
See, the beautiful landscapes and towering peaks we love today, they're literally just a single frozen frame in a movie that's been playing for millions of years. To understand the plot, we have to travel down into the depths. Peeling back the surface, we've got three main layers. We hang out on the outermost crust, which is super thin. Under us is the thick mantle packed with semi-molten rock called magma, and dead center, the core, which is this incredibly dense, ridiculously hot sphere.
So, how do these layers interact? Well, the core is mostly iron and nickel, and the intense heat down there basically acts like a giant planetary furnace. That heat rises up, driving massive, slow-moving convection currents in the thick magma of the mantle. It's this constant, churning engine deep underground that sets the stage for literally everything that happens up on the crust.
Which brings us to part three, internal builders, plate tectonics, and all that pushing and pulling.
Okay, so how does that underground furnace actually build massive structures like mountains? The big secret here is that the Earth's crust isn't a single unbroken eggshell. It's actually cracked into massive, rigid pieces we call tectonic plates. They fit together like a giant spherical jigsaw puzzle. And because they're floating right on top of that churning mantle we just talked about, they're constantly moving. Just, at a snail's pace over millions of years.
And depending on those underground currents, these massive plates do some pretty crazy things when they meet. Sometimes they pull completely apart from each other. Other times, they smash directly into one another in these earth-shattering, slow-motion collisions.
Let's compare those two kinds of movement. Convergent boundaries are your massive builders. The plates collide, rock layers compress, they bend, and they get shoved forcefully upward. That's exactly how we get colossal fold mountains like the Himalayas. But divergent movement, that's when plates tear apart. As they move away from each other, magma rises up from the mantle, cools down, and actually forms brand new crust and deep rift valleys.
Now for part four, external sculptors, weathering and erosion, carving the canvas. So here's a thought. If internal forces are constantly shoving mountains up, why haven't they hit the moon by now? Enter our external sculptors. These two forces team up to wear the Earth right back down. First, you have weathering, which is what physically or chemically breaks rocks down right where they stand. Think freezing water cracking a boulder. Then you have erosion, which is the transportation system. Erosion actually carries that broken, weathered material away using water, wind, or ice. You can really see these sculptors showing off in extreme environments. Out in dry deserts, there's not much plant life to hold the soil down, right? So wind becomes this incredibly powerful, abrasive force. It blasts loose sand against rock formations, slowly chewing away the softer lower parts. That's exactly how we end up with those wild, distinctive, mushroom-shaped rocks. And it's not just the wind. Along our coastlines, ocean waves are relentlessly pounding the shore, day in, day out, with immense force. That repetitive beating gradually weakens the base of the rock until it fractures and collapses, carving out those steep, dramatic coastal cliffs and sea caves we all love taking pictures of.
But honestly, some of the coolest sculpting happens completely out of sight, deep underground. Rainwater seeps through cracks, becomes groundwater, and slowly dissolves soluble rocks, like limestone. Give it a few thousand years, and this slow hollowing out process creates massive subterranean caves, complete with incredibly intricate stalactites hanging down and stalagmites growing up from the floor.
Moving right along to part 5, Earth's evolving landforms, the Grand Gallery.
So when you mix the heavy lifting of our internal builders with the fine carving of our external sculptors, you get a constantly evolving grand gallery of natural architecture. A perfect example? A river system. In their upper course, way up in the mountains, they flow fast, rapidly eroding steep V-shaped valleys. In the middle course, things flatten out, the river slows down, and it acts like a giant conveyor belt, transporting all that eroded material. Finally, in the lower course, it slows to a crawl and deposits all that rich sediment, building vast, flat river plains.
And this isn't just trivia, it directly impacts us. Take a look at the Indo-Gangetic Plain. Why are spots like this absolutely packed with people today? Because millions of years of that exact river deposition have laid down incredibly thick, nutrient-rich soil. These massive geological forces have literally built the fertile agricultural lands that sustain huge populations and entire economies. Which brings us to our final section, Part 6, Sudden Shifts, Natural Disasters, and what happens when time speeds up.
Okay, we've been talking about things that take millennia, but it's time to shift gears, because the Earth can also change in terrifyingly rapid ways. Not all geological changes are slow. Sudden, violent natural disasters are triggered by the exact same internal and external processes we just talked about. But instead of taking millions of years, all that energy is released at once, reshaping the landscape in a matter of seconds.
Remember those massive tectonic plates grinding against each other? Well, sometimes they snag. They get stuck along a fault line, and immense pressure just builds and builds. When they finally snap and release all that pent-up energy, we get massive earthquakes. The ground violently ruptures, land can literally sink, and buildings can be completely devastated.
And these events often trigger a vicious chain reaction. The sudden shaking from an earthquake or even just really heavy rainfall can loosen up weathered rock and soil on steep slopes. Gravity takes over, and suddenly you have a devastating landslide. Massive chunks of earth slide downwards, blocking rivers and wiping out roads and settlements in the absolute blink of an eye.
But here's the thing. We aren't helpless. Understanding these intense forces is practically essential for our survival. By studying how the Earth shapes itself, we can put real disaster mitigation strategies into play. We use geology to pinpoint dangerous fault lines and unstable slopes. That way, we can plan safer settlements, build tougher infrastructure, and set up clear evacuation plans to protect our communities and save lives today.
So, back to that very first question we asked. Is any landform truly permanent? Obviously not. Our planet is incredibly dynamic, caught in this endless loop of creation and destruction. Which leaves us with a pretty wild thought to chew on. If the Earth's surface is continuously being shaped and reshaped by these immense natural forces, what is the landscape you call home going to look like a million years from now? Thanks for tuning into this explainer. Keep that curiosity alive, and I'll catch you next time.